What is quantum physics? Why should we care about knowing what is quantum physics? Do we need to know what quantum physics is? How does quantum physics affect our daily lives? These questions and many more come to mind when one thinks of quantum physics. Which questions should we try to answer first? We will first settle the issue of knowing what we are talking about, quantum physics. Understanding the story of the birth of quantum physics will help us understand what quantum physics is. Quantum physics is the physics of the microscopic world, the world of molecules, atoms, and subatomic particles. It is a branch of physics that was born in the early decades of the 20th century, with its seeds germinating in the late decades of the 19th century. Quantum physics was born out of a mixture of failure to understand certain experiments, and also out of nonsense results when applying classical physics to atoms. Yes, physicists were already familiar with the notion that matter is composed of microscopic packets, the atoms. This notion was initially put forth by the Greek philosopher Democritus, who postulated that everything is built from atoms and the void. Later on, chemists starting in the 18th century with English chemist John Dalton, and after carefully studying chemical reactions and the proportions of reagents that go in and the proportions of the resultant chemicals, correctly inferred that matter is built of individual packets, which he called atoms. Dmitri Mandeleev in the 19th century classified atoms by their chemical properties and arranged them into the periodic table of elements that we are familiar with today. We will see as we go on with our story that the chemical properties of atoms are a direct consequence of quantum physics. Physicists knew that matter is overall neutral, made up of equal positive and negative charges. So after verifying that matter is made up of atoms, experiments focused on understanding the architecture of the atom, basically understanding how the negative, electrons, and positive charges, protons, are arranged in atoms. Enter the New Zealander physicist Ernest Rutherford in the first decade of the 20th century, who shot alpha particles, helium atoms that have lost their 2 electrons, into thin gold foil. Rutherford observed that the alpha particles, positively charged, were deflected from positively charged point particles of much higher charge. The picture became clear now. Atoms are made up of dense positively charged nuclei surrounded by orbiting negatively charged electrons. All this is fine and nice and a source of confidence, so much so that many physicists at the beginning of the 20th century were predicting the death of physics. Their opinion went something along these lines. It's only a matter of a few years when we know all that we need to know about the fundamental physics of nature. We know everything. It's now just a matter of applying our physics to the world around us. And that is exactly what they did. But nasty surprises awaited them. Follow our YouTube channel, Insane Curiosity, to learn more about nasty surprises awaiting scientists even today. Just a decade before Rutherford conducted his experiments, German physicist Max Planck was studying radiation emitted by the so-called black body. In physics, a black body is an object whose peak emission wavelength, or in other words, color, is related to its temperature. Imagine a piece of iron that you throw in a fire. As it gets hotter, it first glows red, long wavelength, and when it gets even hotter, it glows even brighter, but its color will become blue, short wavelength. This glowing piece of iron is referred to physicists as black body. What Planck was pondering was what happens if one were to increase the temperature of a black body even further. The relevant physics known at the time, thermodynamics, predicted that the black body should grow yet brighter but in the ultraviolet. The color of the black body should not only shift towards shorter and shorter wavelengths, but its brightness should become increasingly higher very fast, so that it reaches infinity. But this is nonsense. How can heating an object, basically pumping a finite amount of energy into it, make it emit an infinite amount of energy? This is forbidden by the law of conservation of energy. Planck's success was postulating that radiation or light is quantized in individual packets of energy called photons. The energy carried by each photon is inversely proportional to the wavelength of the radiation, with the constant of proportionality now called Planck's constant. None other than the Albert Einstein used this result to describe the photoelectric effect experiment, another important experiment of quantum physics, for which he later won the Nobel Prize. Other physicists in the early decades of the 20th century applied their physics known to them at the time, classical mechanics and electromagnetism, to the simplest of atoms, the hydrogen atom, one electron orbiting a single proton. Let us put our physics hats on. Classical mechanics says that an object orbiting a center must experience centrifugal acceleration. Electromagnetism says that an accelerating charge must give off radiation, energy. Now let us put one and one together. The electron, a charged particle, as it orbits the proton in the hydrogen atom, will experience acceleration, so it must radiate. So far, so good. However, and here comes the nasty surprise, the radiation emitted by the electron will steal away its energy, making its orbit decrease and spiral towards the proton in a fraction of a fraction of a fraction of a second. So basically, classical physics predicts that no atoms should exist, and by consequence, we too should not exist. This nonsense result was a slap in the face of early 20th century physicists that not all is well with physics, or at the least, there must be something over and beyond the classical physics known till then. Classical mechanics, thermodynamics, electromagnetism, and optics. This new physics became known as quantum physics. Its cornerstone is that all physics quantities that could be observed, the so-called observables, are all quantized. That is, they come in individual, discrete units instead of taking on a continuum of values as in classical physics. Faced with the above, atoms should not exist debacle, Danish physicist Niels Bohr proposed in the second decade of the 20th century his toy model of the hydrogen atom. He postulated that the existence of stationary orbits in which the electron, if it satisfies a certain condition, does not radiate its energy away. That condition is related to its orbital angular momentum, and it dictates that the orbital angular momentum of the electron in this orbit must be a definite multiple of Planck's constant. This toy model was able to explain to a high degree the spectrum of emission of hydrogen atoms observed in the lab. Such work of theory and experiment going hand in hand was the way in which quantum physics was built. Moreover, quantum physics was a group effort in which nearly all physicists working at the time contributed to the endeavor, some more than others, of course. This kind of work continued well into the 20th century, in which quantum theory was fully developed and compared against experiment. Of course, needless to say, experiment, which is science truthometer, agreed with the predictions of quantum physics. Quantum theory is the most successful theory in physics. It has also spawned new fields, material science, think smaller and more power computer chips, LED TVs, solar photovoltaic cells, etc. Nuclear physics, think nuclear power and nuclear medicine, and particle physics, theory to describe the subatomic world and related to how the universe came to exist. See other Insane Curiosity videos to learn more. Quantum theory at the utilitarian level is very powerful and leads to practical results that permeate our everyday lives. However, problems with quantum theory sprung up from the very beginning. These problems are at the interpretation level. How do you interpret the story told by the equations? Keep in mind that the equations themselves are correct and self-consistent. They give specific, well-defined predictions that turn out to be correct when tested experimentally. The problems arise when you try to understand the equations. Niels Bohr remains to this day one of the giants of quantum physics and the father of the most intriguing interpretations of quantum physics. An interpretation so bizarre, but also undeniably true, that it gave Albert Einstein many a headache. This interpretation is known as the Copenhagen interpretation. In a nutshell, the Copenhagen interpretation stipulates that if I don't see you, then you don't exist. At the fundamental level, it states that reality depends on the observer. The role of the observer is paramount in quantum physics. The observer and the act of measurement, such as seeing itself, affects the outcome of the experiment. The reason for this is relatively easy to understand. Imagine going into a dark room holding an unlit flashlight. Turning the flashlight on will shoot photons from it to an object in the room, a chair for example. These photons bounce on the chair back to your eye, and that's how you see the chair. Now, the energy carried by the photon is very small compared to the energy that could move the chair, and the chair remains in place. So the active measurement here did not change our system, the chair. Now imagine that instead of a flashlight, you have a gun that shoots golf balls at very high speeds. You go into the room and start spraying with fast golf balls. One or two golf balls are probably going to hit the chair and may also probably move it too. From the sound of the golf balls crashing on the chair, you will know where the chair was located. But now the new position of the chair becomes unknown. Therefore, the active measurement here changed the system. Of course, in quantum physics, all systems are microscopic, and the measurement tools are also microscopic, leading measurements to messing with the system. The Copenhagen interpretation takes this notion to the max and says that the very active measurement makes a system exist. One might be tempted to say, this is just an interpretation, and it needs not be correct. However, recent experiments done at top quantum optics labs strongly suggest that the Copenhagen interpretation is correct. A very graphic illustration of the apparent absurdity of quantum physics and the Copenhagen interpretation is the Schrödinger cat paradox. In this famous experiment, named after Irish-Austrian physicist Erwin Schrödinger, a cat is put in a closed box with a sealed vial of poison. A radioactive source might decay at random and emit a radioactive particle that would break the seal, thus killing the cat. To an outside observer, the cat has a 50-50 chance of being dead or alive. The way this is expressed in quantum physics formulas, the so-called state function will assign equal weights to the cat being dead or alive. A physicist can do all calculations required and compare it to experiments, and all will be fine. But when the physicist tries to interpret the state function formula, all hell breaks loose. The equation seems to be saying that the cat is dead and alive at the same time. But remember, who determines the truth? It is the act of observation itself, the measurement. The observer will have to open the box to determine whether the cat is alive or dead. Another weird aspect of quantum physics is the so-called particle-wave duality, or the complementarity principle. In our macroscopic world, matter behaves like particles. The ball is here, the bike is there, and light behaves like a wave, cause of the rainbow seen on a DVD's data surface. In the microscopic world governed by quantum physics, an entity, matter or light, will behave as a particle or a wave, depending on the experiment. More support to the Copenhagen interpretation above. French physicist Louis de Broglie, author of probably the shortest doctoral thesis in physics, in which he presented the smallest formula that would later win him a Nobel Prize in Physics, proposed in that same thesis in the 1920s that a particle with a given value of linear momentum, basically mass multiplied by velocity, will have the wavelength of its complementary wave inversely proportional to its momentum. The constant of proportionality is Planck's constant yet again. Experiments done on electrons show that they behave like a wave upon passing through very narrow slits, a behavior seen for light also. Albert Einstein successfully explained the photoelectric effect mentioned before by invoking the particle nature of light. In that experiment, light will behave like small particles, photons. Other weird aspect of quantum physics, such as quantum entanglement, quantum teleportation, quantum encryption, and quantum computing, will probably be dealt with in future videos on our channel, Insane Curiosity.